Hello everyone, this is Sareem from Exam Help Lab. Today I'll be solving Cambridge International AS and A-Level Physics 9702 Paper 2 Variant 3 May June 2022. Starting with question number 1, a solid metal sphere has a diameter of 3.42 with an absolute uncertainty of 0.02 centimeters and a mass of 67 grams, which has an absolute uncertainty of 2 grams. Part A, calculate the density in grams per centimeter cube of the metal. So density has a formula which is mass over volume. The mass is 67 grams and the volume is not explicitly told here, but we can determine that. The solid is spherical in shape as stated over here, and the volume of a sphere is 4 by 3 pi r cubed, where r is the radius and you have been given with the diameter. So your volume of sphere is going to be 4 by 3. The radius is going to be half of your diameter, which is 3.42, and half of it and cube of this. So your volume is going to be approximately 20.94 centimeter cube, and hence you get the value for density as 3.2 grams per centimeter cube. Part B, determine the percentage uncertainty in the density. Percentage uncertainty questions are pretty straightforward as compared to those of absolute uncertainties. So the percentage uncertainty here is going to be the sum of percentage uncertainty of mass multiplied by the times multiplied by the number of times it is being used in the formula of density, because we are calculating the percentage uncertainty of the density. So density is equals to mass over volume. Mass is only being used once because mass is raised to power 1 over here. So mass, percentage uncertainty of mass multiplied by 1, and volume multiplied by the number of times it is being used in the formula. Since we are calculating percentage uncertainty for density, so we need to see how many times mass and volume quantities are being used in its formula. Mass is raised to the power 1, so we multiply the percentage uncertainty by 1. The absolute uncertainty that we are provided with over here is of diameter but not volume. So how many times the diameter is being used in the formula of volume of sphere, which is here? It is being used thrice because the radius or the diameter is going to be raised to the power 3. So we are going to multiply the percentage uncertainty of diameter with 3. So percentage uncertainty of mass is going to be its absolute uncertainty divided by the mass multiplied by 100% plus 0.02 divided by 3.42 into 100% multiplied with 3. So your percentage uncertainty for density is going to be 4.7%. Question number 2, an archer releases an arrow towards a target at a velocity of 65 meters per second at an angle of 4.3 degrees above the horizontal as shown in figure 2.1. When released, the tip of the arrow is a horizontal distance of 70 meters from the target and 1.66 meters above the horizontal ground. The arrow hits the center of the target. Assume that air resistance is negligible and that all the mass of the arrow is at its tip. Part A showed that the time taken for the arrow to reach the target is 1.08 seconds. Now let me tell you, since this arrow is initially held at an angle of 4.3 degrees to the horizontal component, it's going to travel a projectile motion. There are 2 ways to deduce the total time taken for this arrow to reach this center of target. You either consider the vertical or the horizontal part of this projectile motion. Here we'll use the horizontal component of its entire distance that it travels, or the entire projectile motion that it takes. So horizontal distance that the arrow travels is 70 meters. And we can find the horizontal speed, which never changes, and that is going to be this speed, because it starts traveling with this speed of 65 meters per second, but that speed is at an angle of 4.3 degrees to the horizontal part, right? So its horizontal speed is going to be the horizontal component of the speed 65 meters per second. So 65 cos 4.3. So the total time taken is going to be, we are going to use the standard formula since there is no acceleration in the horizontal part of the projectile motion unless stated. So 70 over 65 cos 4.3, and that gives you 1.0799, which is equivalent to 1.08 seconds. Part B, calculate the height of the center of the target above the ground. Now, for the vertical part of the projectile motion, since acceleration due to free fall is not going to be negligible, we are not supposed to use the standard formula that we used in part A, which is distance is equals to speed into time, but 1 out of 4 Soviet equations. Second, when the archer releases the arrow, it travels this projectile motion, alright, and then hits the target. When it is at this position, when the arrow reaches this position, which is the exact same height when it was at its initial position, the displacement, the total displacement of the arrow is going to be 0. Now this position where it hits the target, it is vertically below this position. So this is the vertical distance that I'm first going to calculate. Alright. Now for the entire part, when the arrow gets released until it reaches the target, its initial vertical speed, because if you're considering the vertical part of the motion, the initial vertical speed is going to be the vertical component of the speed 65 meters per second. So I can write that the initial speed is going to be the vertical component with an angle of 4.3 degrees, right? Now the total time taken by the arrow to reach this point from its starting position is what we calculated in part A, that is 1.08 seconds. And the acceleration, because the arrow is going to travel downwards, it is going to be negative 9.81. Alright. So as I mentioned before, that we are going to use 1 out of 4 Soviet equation. So the one that I'm going to use in this part is displacement is equals to ut plus half at square. Now mind that displacement is not the entire distance, is not the total distance that the arrow travels. This is the entire distance that it travels. However, I'm only supposed to use the displacement, which is this one, and that is the vertical displacement. Not just displacement, but the vertical component of the displacement. So the displacement in actual is this one, but I'm going to calculate the vertical part of it, the vertical component of the displacement. So the vertical component of the displacement is equals to, and that's how I get a vertical displacement of the arrow as 0.458 meters. Now I'd like to also mention that displacement is not distance. Displacement is the shortest distance from its starting position until the end. This is the entire distance that the arrow travels from the starting until the target, and the displacement is going to be the shortest from its starting position. The starting position is a position that is at the same height. So this is the position, starting position, and this is the end position. So this is going to be the displacement. However, in part B, we are only considering the vertical part of its motion. So the vertical component of the displacement is going to be this one, and it has a magnitude of 0.458 meters. The question asks you to find this height. Alright, so this is going to be the difference between 1.66 meters and the vertical displacement of the arrow. So we're going to write that 1.66 minus 0.458 meters, and hence we get a height of 1.2 meters. Part C, by considering energy changes, state and explain how the final kinetic energy of the arrow as it hits the target compares with its initial kinetic energy immediately after release. A numerical calculation is not required. So as it can be seen very clearly now, since the height of the arrow in the final position, that is at this target, is less than when it was held at this position. This height is a lot more than this height, right? This height is a 1.2 meters as calculated. Now there is a decrease in the height, which means that there is loss in gravitational potential energy of the arrow. Now energy must be conserved, so this loss in gravitational potential energy means there is going to be a gain in kinetic energy of the arrow. So we can write that Question number 3, part A, define velocity. Velocity is not distance because that's speed. Part B, a constant driving force of 2400 newtons acts on a car of mass 1200 kilograms. The car accelerates from rest in a straight line along a horizontal road. Assume that the resistive forces acting on the car are negligible. Part 1, calculate the acceleration of the car. So acceleration is equals to resultant force on the car divided by the mass of the car. As of now, there is a resultant force of only 2400 newtons because there is only one force that acts on the car and the resistive forces are all negligible. The mass of the car is 1200. So at this point of time, there is an acceleration of 2 meters per second. Part 2, on figure 3.1, sketch a graph showing the variation with time t of the velocity v of the car for the first 20 seconds of its motion. So as stated over here, that the car starts to accelerate from rest, which means that it has an initial speed of 0 meters per second. So this is the first point that I'm going to mark on the graph, that at t is equal to 0, it has a velocity of 0. Alright. Now, it also says that it travels with acceleration and it is going to be constant throughout because there is no other force that acts on the car other than the driving force, which is of 2400 newtons. So there is constant resultant force, hence constant acceleration. So there is going to be a straight line through origin with positive gradient. The positive gradient indicates that the object or the car is accelerating, and the straight line indicates that it is constant. It is not changing, it's not varying. All right. Now they ask you to mark on the graph until 20 seconds, until t is equals to 20 seconds. So the final speed is what you could calculate because you have been given with all the data required, which is your initial speed is 0, time is 20 seconds, and the acceleration is 2. So you can use the formula v is equals to u plus at, and you get the final velocity at 20 seconds, and it's equal to 40 meters per second. So the second mark is going to be 20 on the x-axis and 40 on the y-axis. So here, and there's going to be a straight line with a positive gradient until this point. All right. Part C, in reality, a resistive force due to air resistance acts on the car. In part B, this resistive force increases with speed until it becomes equal in magnitude to the driving force at time t is equals to 12 seconds. Part 1, on figure 3.1, sketch a second line to show the variation with time t of the velocity v of the car for the first 20 seconds of its motion. Label this line B. Alright, so the resistive force starts to act now on the car, and it increases until it's equal to the driving force, which was 2400 newtons. And this is the moment that when the car starts to travel with constant velocity, because both the forces, they act in the opposite direction and they are going to get balanced. Since resultant force on the car will now decrease because both forces act in opposite directions, the acceleration will also decrease to 0 acceleration when it starts to travel at a constant speed. The gradient of the velocity time graph represents the acceleration on velocity time graph. So decreasing gradient because the acceleration is going to decrease until 12 seconds. So at this point of time, both the forces on the car, they are going to get balanced, 2400 newtons of driving force and 2400 newtons of resistive force, and that's when the car continues to move at a constant speed. So let's suppose that it had reached the speed of 25 meters per second, and it's going to continue at this constant, very 25 meters per second speed until t is equals to 20 seconds. And the acceleration is going to decrease, right? So a decreasing gradient on velocity time graph is going to look somewhat like this. It is initially going to lie on the exact same line, but it is going to have a curve here. So it's going to be somewhat like this, right? And then it's going to continue with a horizontal line on the graph. This part of the graph indicates decreasing gradient, and this part of the graph indicates there is going to be zero, gradient of zero, because the car continues to move at a constant speed until 20 seconds. So this is 20th second, and this is going to be the 12th second, and this starts from zero. All right. Part 2, at time t is equals to 20 seconds, the driving force is increased to 3000 newtons and remains constant at this value. Describe how the velocity of the car changes due to this increase in the driving force. So increase in driving force means that the resultant force on the car increases, which in turn means the car starts to accelerate, but due to simultaneous increase in resistive force on the car again will have terminal velocity, but this time it is going to be an increased one. So we can write that due to increase in the driving force, the car is going to accelerate, but due to also rise in the resistive force that acts on the car, the new terminal velocity is going to be a higher one or an increased one. Alright, terminal velocity is the stage where all the forces that act on the car, they get balanced and the car continues to move at a constant speed. Question before part A mass m moves a vertical distance in a uniform gravitational field and gains gravitational potential energy. The acceleration of free fall is g. Use the concept of work done to show that your gravitational potential energy is equals to mass into g into change of height. So we can write that gain in GPE, which is gravitational potential energy, this is equals to the work done by mass. And your work done is force multiplied by displacement, or distance in the direction of force. Alright, so your force is going to be further broken down into mass into g, and displacement is the change in height, so mg into change in height. Part B, a 0.6 kilograms mass is attached to a string, which is wrapped around the wheel of a generator as shown in figure 4.1. The mass is held stationary above the floor when released. The mass initially accelerates and then falls at a steady speed and spins the wheel. The generator causes a current in a resistor. A resistance is negligible. State the main energy change when the mass is falling at a steady speed. Because the mass falls, its GPE definitely is going to decrease, and the resistor is receiving the current, and resistor is the only component that is in the circuit, so it heats up. So the energy change at last will be from gravitational potential energy to heat or thermal energy. Part C, when falling at a steady speed, the mass in B falls through a vertical distance of 1.4 meters in a time of 4 seconds. This causes a current of 90 milliamperes in the resistor. The resistance of the resistor is 47 ohms. Calculate the rate of work done by the falling mass. So rate of work done is power. Energy transferred. The energy that is transferred is loss in GPE because the mass starts to fall. So loss in GPE, that's your work done, divided by the time taken for this fall. Now loss in GPE is equals to mass into G into H. The mass of the block is 0.6 kilograms from the previous part, multiplied by 9.81 into the change in height, or the vertical distance that the mass traveled is this, so 1.4, divided by the time taken for this change of vertical distance is 4 seconds. So the rate of work done is 2.1 watts. Per to the power dissipated in the resistor. So power dissipation has its own formula, that is I square R. The current that runs through the resistor is 90 milliamperes, so you need to convert that to amperes, multiply it with 10 to the power of negative 3, square that, and multiply it with 47 ohms. You get the power dissipation of the resistor as 0.38 watts. Part 3, the efficiency of the generator. Now the only purpose of the generator that could be seen is running the current across the resistor. And the resistor always heats up whenever some current runs across it. So the total power output, that is in the form of thermal energy, divided by the total power input, that is the amount of work that was being done by the mass to bring up that thermal energy, that is the 2.1 watts from this part, multiply it with 100%. So you get the efficiency as 18%. Question number 5, part A. Parallel light rays from sun are incident normally on a magnifying glass. The magnifying glass directs the light to an area A of radius r, as shown in figure 5.1. The magnifying glass is circular in cross-section with a radius of 5.5 centimeters. The intensity of the light from the sun incident on the magnifying glass is 1.3 kilowatt per meter square. Assume that all of the light incident on the magnifying glass is transmitted through it. Part 1. Calculate the power of the light from the sun incident on the magnifying glass. So power is equals to the incident intensity into the cross-sectional area through which the light is transmitted. So your intensity is 1.3 multiplied by the area, since the area is not directly given, but the lens is in the shape of a circle, so we can find the area of the circle that it is transmitted through, and that is pi r squared. The radius is in centimeters, so you need to convert that to meters and square that. So you get the value of power as 12 watts. Part 2, the value of r is 1.5 millimeters. Calculate the intensity of the light on area A. So again, intensity is equals to power divided by area. Your power calculated in the earlier part is 12, and this area over here, this region, is in the shape of a circle, so pi r squared. The value for small r is 1.5 millimeters, so convert that to meters. 1.5 into 10 to the power of negative 3 and square of that. So intensity is 1.7 into 10 to the power of 6 watt per meter square. Part B, a laser emits a beam of electromagnetic waves of frequency 3.7 into 10 to the power of 15 hertz. That's your frequency in a vacuum. Part 1 showed that the wavelength of the waves is 8.1 into 10 to the power of negative 8 meters. So the formula that connects all these quantities is speed is equals to frequency into wavelength. Speed of all electromagnetic waves in a vacuum is 3.3 into 10 to the power of 8. Divide that by the frequency, that is 3.7 into 10 to the power of 15 hertz, and you get 8.1 into 10 to the power of negative 8 meters of wavelength. Part 2, state the region of the electromagnetic spectrum to which these waves belong. So this is the ultraviolet wave. Part 3, the beam from the laser now passes through a diffraction grating with 2400 lines per millimeter. A detector sensitive to the waves emitted by the laser is moved through the arc of 180 degrees in order to detect the maxima produced by the waves passing through the grating, as shown in figure 5.2. Calculate the number of maxima detected as the detector moves through 180 degrees along the line shown in figure 5.2. Show your working. So the formula for diffraction grating that we use is pi n is equals to d sine theta, where d over here is equals to 1 over the number of lines per millimeter. So over here it's 2400. So the value for d is going to be 4.167 into 10 to the power of negative 4 millimeter. You need to convert that to meters. So it is going to be equal to 4.67 into 10 to the power of negative 7 meters. You have got the value for d. Now the value for lambda, which is the wavelength, it is equals to 8.1 into 10 to the power of negative 8 meters. The value for n is what you need to calculate. That is the total number of maxima that forms. Now if you rearrange your formula, n is equals to d sine theta over lambda, where your theta, the value for the angle value for theta is going to be 90 degrees, because the number of maxima above this incident ray, this is the incident ray, so the number of maxima that the detector detects here is going to be equal to that in this lower region. All right, and an additional maxima is going to be this one. This is going to be at an angle of 0. This is the additional maxima that forms. All right, so n is equals to, the value for d is 4.167 into 10 to the power of negative 7. Multiply it with sine 90. because the detector moves through 180 degrees of arc, so the final position of the detector is going to be here. Suppose this is the initial position, so it moves through an angle of 90 degrees, so I considered sine 90 here, divided by the wavelength, that is 8.1 into 10 to the power of 8. Over here you'll be getting some value in decimal. You need to take the whole number of it. Somewhere you will get something like 5.1 something, so you need to take the 5. Now this means that there are going to be 5 maxima forming here, which also means that there are going to be 5 maxima on the lower region, and we are also going to add 1 maxima that forms here to our sum of maxima that forms here in figure 5.2. So it is going to be 5 into 2 times and plus 1. So the total number of maxima is going to be 5 into 2 plus 1, and that's 11. Alright. Now part 4, the laser is now replaced with one that emits electromagnetic waves with a wavelength of 300 Newton meters. Explain without calculation what happens to the number of maxima now detected. Assume that the detector is also sensitive to this wavelength of electromagnetic waves. Now according to the formula, that is n is equals to d sine theta over lambda, the number of maxima is inversely proportional to the wavelength. Now 300 Newton meters is a longer wavelength than the one that we were using in the earlier part, and that was of 8.1 into 10 to the power of negative 8 meters. So increase in wavelength means that the number of maxima is going to decrease because they're inversely proportional. So we can write that Question number 6, part A. On figure 6.1, sketch the IV characteristic of a filament lamp. So this is how the grating goes. It passes through the origin. Alright. Now, part 2, explain the shape of the line in A part 1. Alright, so when the current starts to increase, which also means that the temperature is increasing, that is of filament wire, the resistance will definitely increase, and resistance has a formula of V over I, which means that resistance increases means the ratio of V to I will increase, definitely, or you could also say that the ratio of I over V will decrease. Alright, so we can write that part B, a conducting wire has length 5.8 meters and a cross-sectional area of 3.4 into 10 to the power of negative 8 meters square. The resistivity of the metal of the wire is 5.6 into 10 to the power of negative 8 ohm meter. Calculate the resistance of the wire. So resistance is equal to resistivity into length of a cross-sectional area. The resistivity is 5.6 into 10 to the power of negative 8 into length is 5.8. Divided by the cross-sectional area of the wire, that is 3.4 into 10 to the power of negative 8, and you get a resistance of the wire is 9.6 ohms. Part C, a resistor of resistance R is placed in a circuit with a cell of negligible internal resistance, 2 switches S1 and S2, a second resistor of resistance 2R, and 3 elements, 3 ammeters X, Y, and Z. The circuit is shown in figure 6.2. The reading on X is 1 ampere when S1 is open and S2 is closed. Complete table 6.1. When S1 is open and S2 is closed, which means that this entire path is complete. Alright, till here it is complete. This is the path. This is the complete path. And the ammeter X and Z, they are in series, they are connected in series, so they are going to share the same current. When 1 ampere of current runs across X, this means that 1 ampere of current will run across Z as well. So I'm going to write 1.0 here, and that across Y is going to be 0 because this connection is incomplete, so there's going to be no current that flows across this path, so 0 amperes. Now when S1 gets closed and S2 remains open, resistance of entire loop is going to decrease from 2R to a single R, because the last time this was open and this was closed, so the total resistance of the circuit was 2 times of capital R. Now this remains open and this gets closed, so the total resistance of the circuit has decreased to half of the original resistance. This means that the current across the loop is going to increase by 2. So I'm going to write that 2.0 amperes of current flows across X. And since this S1 is closed, so this time this is the path that remains complete, this highlighted one, and this is the path which remains incomplete. So there's going to be no current that flows across Z, so it's going to be 0 amperes here. Now when 2 amperes of current flows across X, 2 amperes of current will flow across Y as well, because ammeters X and Y, they are connected in series. So 2.0 amperes here. Now when both switches S1 and S2 they are closed, the combined resistance of circuit is even less than just R, because the combined resistance of circuit this time is going to be 2R into R over 2R plus R, and that is equals to 2 by 3 of original resistance, which is capital R. So it's going to be even less than this single component's resistance. So the current is going to increase from 1 ampere, which was the original current that had flown across the emitter X. It will be increased to 3 amperes, 3 times of the original one. So it's going to be 3 amperes here. Now since both these parts are complete, and this component X is connected in series with the parallel connection of these two, so the current over here that flows across is going to be 3.2 amperes. This will split into 2 parts. Now the greater percentage of 3 amperes will flow across Y, because there is less resistance as compared to this one. This is 2 times of R and this is just single R. So the greater percentage means that 2 amperes, I'll assume that 2 amperes will flow across this one, and the remaining 1 ampere will flow across this one. So I'm going to write that 2 amperes flows here and only 1 ampere of current will flow across that because of higher resistance. So less resistance means that it is easier for the current to flow across that path, and higher resistance means that it will try to change its direction to the path that has less resistance. Question number 7, part A. Fluorine is an isotope that decays to an isotope of oxygen by the emission of a beta plus particle. Part 1 complete the nuclear equation for the decay, including all the particles involved. So all the particles involved and 3 marks of the question. So we are not just going to write the beta plus and the other particle, the other isotope that's released, but a complete nuclear equation. So beta plus particle carries almost no mass and a charge of +1, and the isotope that is released is of oxygen, so O. Now we have to balance the charge and the mass, so it's going to be 18 again here, and then 8 plus the other particle that's released in the beta plus decay is neutrino. This will get you 3 credit, otherwise you'll get only 2 credit for this part. Part 2, a quark in the fluorine 18 nucleus changes flavor during the decay. State this change of flavor. So in beta plus decay, a proton changes to neutron. So an up quark changes to a down quark. Part B, a hadron has a charge of -2e, where e is the elementary charge. Part 1, state and explain whether the hadron is a meson or a baryon. So a hadron is baryon because mesons, they have got a charge of either 0 or plus or minus. Alright, part 2, state a possible quark composition for the hadron. So this hadron carries a total charge of -2e. So we can say that an anti-up quark, which carries a charge of -2/3e, an anti-top quark that again carries a charge of -2/3e. Lastly, we could take an anti-charm quark that also carries a charge of -2/3e, and this combines to a charge of negative 2e that is over this hadron. So that was the end of the paper. Thank you for watching.